let's try to make this presentation more interactive and less academic. So let me introduce myself. So I'm Olivier Maret, coming from Hitachi Energy. Yeah, it's working very good. So we have a factory in Jumet, so it's close by Charleroi. I am with my colleague Mahmoud here. So Mahmoud, yeah. So we have an international company. Alors, where do we come from? So actually, we have a long history of power quality. Because we are one of the former division of Les Assec. If the most experienced people here know Les Assec, a very electrical company, Assec, Atelier de Construction Électrique of Charleroi. So we are from the capacitor division of this company created in the 1920. And so we have a long history of innovation and I would say expertise in the power quality. For example, we were the first company in the 1970s to develop the dry capacitor, low voltage dry capacitor technology. So before it was all impregnated capacitor. So we made the development here in Belgium. So this is interesting to mention. In the 90s, we were one of the first company to develop active filters in the market, so to remove the harmonic pollution actively in the market. So we were also pioneer in this field. And nowadays we developed, I would say, the next level of three-level inverters for power quality. So we have in Belgium, I would say, some pioneer and high technical company. We belong on this type of company. Alors, briefly, what is the power quality? And I will make a short bridges with the previous presentation. So this morning with Agora, we were talking about, I would say, regulation, which is changing because we want to have the loads and the application factory cleaner and cleaner, greener and greener. So evolution of the regulation and standards. We were talking about battery BMS. Peter, you were talking about batteries. So batteries, it's one of the product that we developed here. It's battery energy, battery BESS, battery energy storage system. So why do we do so? Why do we need batteries? And BMS, it's one of the brain of the battery, the thermal aspect of battery we discussed. And we were talking about the EMC laboratory. So we were talking about immunity test. And so I remember that they were explaining that EMC tests could be fast or long. In power electronics, when we use power converters, so with IGBTs, with MOSFETs, don't believe that you are going to succeed a test in 1 month. Sorry. Alors we are not talking, so it was a nice example with a smoothie machine. So here in industry, we are talking about tens of kilowatts, hundreds of kilowatts, megawatts, and we need power electronics. So we are in a totally different world with significantly larger power, and so we need to control those powers. I would say modern switches, so semiconductors, IGBT for example, which generate by the switching a lot of EMC problems. And so this is a link with what we talk. And so we have immunity and we have emission. Both aspects have to be considered at the same time. So for just to introduce what we are doing in our factory, but also in the group, because we are not only the only factory in Hitachi Group. We belong to a product line within a product group, within a division, and there are different divisions in Hitachi. This is a mammoth, big company. So we are very small in power quality. But in Jumet, we are what we call the technical lead center. So that means that we have the R&D team responsible for the line of product that we offer to our customer, and I am the product manager for the low voltage power quality parts. Alors, what we made in Jumet, so we developed, I would say, the low voltage capacitors in the 70s. We still have those products in our range. So it is capacitors, low voltage capacitors, that when you put together the capacitor, you can produce a capacitor bank. So switch with thyristors or contactors. So this is to correct the power factor. So we developed power factor relays. So this is the brain of the capacitor bank to switch on and switch off the capacitor to correct the cosinus phi. We developed in the 90s a range of active filters. So active filter, it's power electronic based device with IGBT to remove the harmonic pollution. And I'm going to introduce what typically are the problem of harmonic pollution. So an active filter can do also power factor correction, load balancing, neutral current removal. So this is a very advanced device. Recently, we developed battery energy storage solutions. So I will present some interesting case studies. So it's always better to talk about application because so we can be more interactive. Alors, we are doing other products in our factory because we are also what we call a feeder factory. So we provide, I would say, some sub-components to other factory which will in turn produce, for example, DC capacitors for high voltage DC transmission line. Because nowadays, when we produce, I would say, wind energy in the North Sea, and we want to bring this energy down to Munich, for example, we need 4,000 kilometers of line, and the best way today in the future, the best way is to use DC line, so high voltage DC line. So we are talking about 800 kilovolt or 1.2 million volt DC line. Also in Belgium, the shore connection to the North Sea to Brugge is made with a DC line. The advantage is that you can have it underground. Alors, it's more expensive than on air, but you can transport as much power with less incidence in the environment, for the neighborhood and so on, less separate. But okay, this is a cost of investment. So that's not part of my part. Let's go back to power quality. Alors, here so this is a high-level schematics, and we're going to focus on 3 points. Alors, where is the pointer? Here. Alors, here, just after the user, so industry of building. So we have some quality issue, power quality in the talk. I will explain a few. And we have many solutions at low voltage side. So it's always better to solve the problem where the pollution is coming from, as close as possible to the source of pollution, than to take care about the pollution after long transmission line where all the pollution can pollute with EMC and so on. So just fix the problem as close as possible to the source of the problem. And with the battery energy storage solution, we can have, I would say, a battery energy storage solution at the load side. So then what is the advantage? So it's peak here. Okay, peak control demand. So that's very important. Just a practical example. Here in the parking, we have nowadays 4 or 5 battery charger for electrical vehicle. Let's say that in 4 years with the car policy, you will have all the people with electrical car. How are you doing? So then you need to install 40 more charger. but your infrastructure here is made with, is existing, so you will try to use your electrical, but with this extra demand, or you change your electrical power supply, so that means that you need to reinforce your line, ask to Elia, Ores, and okay, I need 2 megawatt instead 1 megawatt, so then, okay, next 10 years, okay, no, this is, it's in 2 years, okay, but yeah, when you order a transformer, this is 2 years delivery time, but it's not only the transformer, it is the feeding line, it is the switchboard, it is everything, and then, okay, 10 million, oof. Do you really need an electrical vehicle? But yeah, because that's the practical, so peak shaving, how to manage it and how to better manage, I would say, the source of power. So, for example, I was working with the public transportation. So many cities nowadays, the bus are electrical vehicles. So this is a bus depot, and they need to charge the bus. So here we were talking about a fast charging, so the thermal aspect. So here we would like to charge in half an hour, and after to have 2 hours cycle. So this is a C4 or C5 charge of battery. Oof. So a lot of thermal issues. So here, yeah, but that's true. That's true. I confirm it's really true. Alors, so new loads. So battery chargers. So how can we optimize the system without having to reinforce an existing installation, which is very expensive, long delivery time. So this is not compatible anymore. We need to find solution. Many customers come back to us, okay, I want to optimize my self-consumption. So nowadays I have a roof of solar panel, but okay, but when there's no sun, how can I improve and put my consumption in line with my production? So that means also that there are some technical solutions with a limited extent, but we need also to think that we will have to adjust our way of living. It's not possible today to say, okay, in the future I will travel as I did in the past with a Ryanair ticket, 40 euro to go to anywhere else. Okay, but it's very good. But is it something reasonable to take Ryanair and at 50 or 60 euro ticket to go, I don't know, to Sofia? And in train, it will cost you 300 euros. So here, this is also a reflection. If we want to be more friendly, we will have to adjust, do more video conference and so on. I don't really like video conference, but I prefer to be from. Okay, that's it. But okay, so from time to time, I can accept it. And yeah, and we were talking about with the first presentation, Marc. The regulation. Every time you connect a battery system in a network, you need to be compliant with the grid code. And of course, there's one grid code for every country, in Belgium, in France, and so on. And they are, of course, different. And so if you need to, so it's a point also that we need to consider. Okay. Alors, just you have understood the problematic, okay, but what is the problem exactly? What are the problems? So here, this is the range of product I give it for, because are you going to distribute the presentation? So very good. So if you need to have more details about our product range and so on, I give you the details here. I will quickly go to, so here, this is the range. So if you want more details, I can explain. Here, it is just to explain what we face today. So with renewables, so we were talking about renewables, wind, solar, very good. But actually, before that, the modern loads consume less energy than before. Just take the LEDs. So today, when we go to the shop, we don't buy incandescent lamps, so it's not existing for years, but even fluorescent tube, it's LEDs. And here I just gave. Oh, the pointer is slower than my. So here we talk about THDI. So THDI is total harmonic distortion in current. We have in current and in voltage. And what is this? It's an important aspect, especially for EMC. If THDV is 0, that means that we have a pure sine wave, no pollution. Higher is the THDV or THDI, higher is the pollution. And so here it's just to show you, for example, your computer. This is the current that your computer draw from the network. And here we have a THDI of 140%. Alors, this is not coming from Hitachi, this is coming from a public lecture. You can find it on internet. So here, this is a light dimmer lamp. So you see how distorted is the current. And for LEDs here, the dimmer, very good. You change the dimmer, but sometimes you need some sound. This is very likely coming from that because the content of harmonic, and then I make the parallel with the emission and EMC regulation. So higher is a harmonic pollution. So what is an harmonic? It is a multiple integer frequency of the fundamental. And so because we have repetitive with Fourier theorem, we have only harmonic. We don't have interharmonic, except it in some loads, but I will make simple. In most of the modern loads, we have only harmonic. Alors, when we have 200 or 360% of THDI, that means that we have more harmonic current, 3.6 times than the fundamental. So that means that we have 3.6 times more harmonic than the fundamental. Alors, okay, good. I don't care. I can live with that. But the problem is that with the Ohm's law, if you have a current which is non-sinusoidal, it will generate a voltage which is non-sinusoidal. And if the voltage is distorted, all the other loads connected to the same grid will be disturbed. And so higher is the current pollution, higher is the THDV, and more you have pollution. And that's the problem. It's because with the immunity and emission, if the level of pollution is too high, then we start to have some problem. So today, the modern load, motors, LEDs, computers, any loads you can, use power supply, which are non-sinusoidal, and so the harmonic pollution is increasing in average. And so we need to have a look to that, because when the level of pollution reaches a certain level, and this level is lower than the immunity level of what the equipment should be. So I take an example. If immunity is 12%, this is most of the level given in the EMC standard, the 61,000, IEC 61,000 that we have seen. So immunity is around 12%. But most of the load that you have in industry or at home, if you have more than 6-7% THDV, you start to have some problems. So that means that you have misfiring, you have overheating, you have sound, because harmonic will generate, I'd say harmonic 9 or 10, it's 450 hertz. It is purely the the sound of music, and it is perfectly audible. And so we have some customer which call us, oh, my transformer is singing. So singing installation, that, no, but it's the technical words. Huh? So it's not opera, but when, yeah, it's just one, it's one tone of music, so it's, but when you have an installation which all of a sudden, when you start some motors and the sound, everything is stopped, what's happening? So the people are really, really afraid. Then it is just sound, but sound may generate overheat, cables which are too hot. that's good. You have a plant, I don't know, hundreds of motors, kilometers of cables, and you cannot touch your cable because they are hot too much. So this is most of the time related to harmonic current. So even I have seen some transformers which were burning with just 50% of the load. So a transformer of 1 MVA, for example, 500 kVA, which the temperature was too hot. So it's not at full load that you have such a problem. Alors, in industry, you have what we call variable speed drive, which nowadays, so it's very good. We change the direct online motors by variable speed drive, so we do 20, 30, 50% of energy savings because you just switch on, switch off your motor when you need in your process. But the current that you draw from the current, you see it's 53% THDI, generate a massive pollution, and so you need to do something. So modern loads, I'm not talking about renewables yet. I will arrive, don't worry, I will arrive. I see that they are waiting for renewables, so we're going. But here today, the change of loads, with more efficient loads, generate more harmonic pollution, and we need to take care about it. Alors, I will give some examples. So here, it's an opera house. So this is the lifting jack, so yeah, opera, so we were talking about music, so I was not thinking about that. And so here, this is the current drawn by the jack, so this is the show room. You can lift up and lift down, so this is the Opéra de Liège, so in Belgium. And so we were, the loads were, so here you see, we represent the motors with a variable speed drive. And what was happening, so with this current, it generated disturbance, and so the LEDs, the magnificent and beautiful central light in the showplace were just flickering. So people were not very happy. It was not very comfortable for the people. And so here we offered an active filter PQFS. And so after filtering, we had a current which is very closer to the sine wave. Alors, so here it's also an optimum. What is the cost of investment in an active filter, and what is the target? You were talking what is the target to reach in terms of temperature in the battery. So here, what is the target of THDV or THDI we need to reach, and so we can size an active filter. Another example, so here it's also a water pump. Alors, what was the problem behind here? It was during the World Cup, not in Qatar previously, so everybody, all the people were in the TV screen to watch the TV. And when the pump were working, because it's in the middle of the village, all of a sudden the disturbance, so the emission of harmonic were making the movie so people could not watch the football match. So it was a revolution. So yeah. Yeah, but it's real problem. So I'm not talking about. Alors, so here, so harmonic pollution, so here it was not a problem for the installation itself, but for the neighborhoods, because harmonic are coming from the feeding line. So this is conducted and radiated pollution. And so here you see the current waveform. So here it's typically a 6-pulse variable, what we call a 6-pulse variable speed drive. And so after harmonic mitigation, compensation, we reduce to a very low level. So here we had a THDI of 30%, and we get down to 5-7%. It was not necessary to go to zero. We can go to zero, but okay, then what is the extra cost of to go to zero? But maybe we need to double the number of active filters or to add an extra equipment. So then it is an optimum technico-economical solution. Alors, I take also this example because here, that's important. You have here the apparent power before and after, and you see that the the cosinus phi have been the cosinus phi normally is not changing, but the power factor change. In many applications today, we have a capacitor bank which is specified by default because it's a well-known topics. But variable speed drive today doesn't require any power factor correction because the cosinus phi is already good. It's only the harmonic content, which is purely reactive power, which need to be addressed. But harmonic, it's at harmonic 5th, 7th, and so on, so not at fundamental. And so this is a very common mistake to still specified capacitor bank, which will never switch on or switch off. You need an active filter. And then you are going to reduce the number of kVA because simply you reduce the current, you reduce the harmonic contents. Okay, just a small comment. Alors, now I'm going to take about another application, and I'm coming with a renewable. So this is a wind park. So here it... solar park, yeah. Wind is coming, yeah, correct. So wind is... Thank you. But it's in my bag, so... Alors, with the this is a solar in Bulgaria, and actually, what is the problem here is that during the night, the solar park is reactive capacitive. So in industry, we have reactive inductive load. Transformer motors are reactive inductive because this is induction machine. You need to create a magnetic flow. So this is reactive inductive. But here, during night, because all of the cables, which are basically capacitors, this is reactive capacitive. So you have two type of reactive energy, reactive leading or lagging, or capacitive and inductive. And here during night, it was reactive capacitive, but during day, when we produce power, because of the line, I don't know, it was reactive inductive. So we have on the same side, I would say a low power factor, reactive and inductive. Alors, here, with the grid connection, you can only, so the solar plant owner got the authorization to correct to the Bulgarian grid only with a power factor nearly unity, 0.98 or 99. So, alors, small comments, power factor is the target, and you have an energy meter, which count the energy that you consume, active and reactive in industry. But you could have a cosinus phi 0, but if you have no energy consumption, you don't pay penalty because your energy counter doesn't turn. So many customers come back to me, oh, Olivier, I have a power factor 0.1, and I will die tomorrow. No, you will not die because you pay nothing. You do, no current, no bill. But here, during the night, we were talking about, let's say, 300, 400 kVAr of energy capacitive. So then it was not neglectable, 340. So it's half a mega MVA of load. So then the utility here imposed to do something. And during the day, the power factor was not so low, 0.9293, but we needed about 600 kVAr. So here we proposed a special capacitor bank with both reactive and inductive called Dynacom, dynamically controlled capacitor bank. Alors, yeah, here it was in the middle of a countryside, so we had a IP50 rating. We had to do anti-snow building with air cooling and so on. So another type of application with green energy, because the rules, so the grid code impose a very high power factor. In Turkey, because the grid is very totally saturated, the target power factor is 0.995. In India, we have 0.998, so we are very close to 1. So they really want to reach the unity because of saturation of the grid. Okay. Here, a wind park. So here again, this is a wind park in Australia. And here, you have to consider that when you connect a wind farm or a solar park to the grid, the constraints are extremely high in terms of power quality. So here, wind turbine, so you see this is 6 times and 7, so 15 times 1.5, so 22 megawatt. And you see that we produce 1.8 amp of harmonic 3, and we were also above harmonic 5 at 66 kilovolts. So that was too much. So if we do the calculation, we are talking about 2 amps, 100 kVA-ish, 200 kVA-ish, out of a range of 22 megawatts. So here, we have 22 MVA, and we want to control 200, 300 kVA of harmonic power quality, I would say harmonic. Here it was harmonic. So the solution here was to install an active filter connected to the 66 kilovolt to reduce the harmonic pollution. So here I gave some example of, to make the parallel with the EMC regulation and compliance with what we can do in power quality. Industry, it's typically the water plant in the Netherlands, or Opera, it's building a commercial application. So we have solution to clean the network. Is it okay? You are my timekeeper, so I will speed up. Okay. Alors, let's go to the next range of product that we have. It's battery energy storage solution. So here we will make the link with battery with BMS. Alors, what we offer, we can offer the inverters. We can offer the full turnkey solution. Alors, what is a turnkey solution? So this is, maybe I will show. So here it depends of the range of power you need. So we can provide a cabinet from 30 kilowatt to 100-ish kilowatt. Alors, we have to mention, so here we mention kilowatt, but actually it is kilowatt and kilowatt hour, because we have the power of the inverter for the charging of the battery and the value of the battery. And so this is two values. We assume here C1, so that means that we have the same rating of the inverter than for the battery. So here 30 kilowatt, it's 30 kilowatt inverter and 30 kilowatt hour battery, so it's C1 charge. So we have different type of solution depending of the power we need. Alors, I'm back here, and we have interface. We can connect this interface to a cloud, so we can have access to the distance of the state of charge, state of discharge, all the parameters of the battery. And we need to have an interface. So the BMS of the battery are somewhere here. So this is embedded in our delivery. So we interface with the BMS. And we need an EMS, energy management system, which is higher level. So that is really the brain of the network. So Hitachi Energy can provide it. It's not from our factory, but we need a system which tell the battery energy storage system, charge the battery, discharge, so we need you to provide, or we need to charge. So our system will not by default decide by himself, okay, I will charge or discharge my battery. No, this is coming from a system. We can also do power factor correction, so we can inject reactive energy as well. And so this system will interface with the connection with the grid to avoid the peak shaving, or to optimize the current here, with solar and electric vehicle charging. Alors, yeah, diesel generator, because now with a battery, I have I selected an example. We can remove a diesel generator, which are hot backup for some application. For example, in hospitals, you need to have, I would say, what we call hot backup, because in term, if you have a breakdown of the network, but if you are in the surging operation room, you need to continue to operate. So there are critical loads, but also in banks, in data center. When you have a bank, you cannot stop the computer like that. No, it's not suitable. Okay. Alors, yeah, so here, this is the product we have. So we have also outdoor solutions. So in the graph, I was showing you indoor solution, but we have also outdoor solution with a combo. So you have the batteries here and the inverters and the interface protection and so on. But we can also have larger power with separated a container with batteries, a container with charger, and you see the air conditioning units here for the cooling down of the batteries. Okay. Alors, I will let's discover together. Oh, the yellow. So what's happening with the yellow? So, okay, I don't know. This is the mystery of the computer. Alors, I will give an example of a battery energy storage system with a commercial building. So here, it was mainly for maximize the self-consumption and also peak shaving, with the industry, with e-mobility, and supply network company. So here it is a center for logistics center in Norway. So you see that they equipped all the roof with a photovoltaic panel, and so you have the technical value. So here, so we installed a 200 kilowatt inverter for 60 kilowatt hour battery, because the target here was to maximize the self-consumption of 1 megawatt peak solar install, and peak shaving with this installation. So we can do both with one installation. Alors, you see 1 megawatt peak shaving, enfin 1 megawatt solar plan, and we installed 200 kilowatts, so it's 1/5, 20%. It's enough to do an efficient peak shaving. Alors, how it looks like, but you have the inverter, the DC protection, and the BMS and battery. The BESS brain is also located here, and the batteries are located here. And for cooling, you see that we have a grid in the front here to have a good cooling of the batteries. Alors, here, this is another application. This is a sawmill wood factory, also in Germany, where also we have a massive solar roof. So the peak shaving, so here the utility didn't accept to so in Germany, you need to have the auto consumption as much as possible, otherwise you pay a huge penalty. And here we install 30 kilowatts, 68 kilowatt hour to maximize the self-consumption and avoid the peak shaving. So this is very similar, but in industrial, very similar to the distribution center, but in industry. And here it was relatively compact solution, one cabinet indoor. Alors, here in the Netherlands, so it's also a green, I would say, energy building. You see on the roof, this is all solar park. So target is also maximize self-consumption and peak shaving. You see that peak shaving and optimize the energy with somehow a limited battery capacity, because we are talking about 1 megawatt hour peak, 1 MVA, 2 MVA transformer, but with 200 kilowatt inverter and with hundreds of kilowatt hour, it's possible to achieve most of the target. But it's not, we are not yet at the point that to store energy during the day because of solar and to running the installation during night. So by far, it's not the case yet. And due to the cost of the battery, I guess it's not economically feasible to have the full autonomy of energy with renewables. Okay, I would like, but in industry, it's a dream. It's a dream. With wind energy, with a massive wind farm in the North Sea, maybe, but then we need to bring the energy from the sea to the onshore. When we will have 20, 30 terawatt of wind energy, and because there are always some wind in the North Sea, then we can think differently. Alors, here we talk about electrical vehicle charger. So here the target was peak to avoid peak shaving to reduce the peak. So here the combination of the battery plus, I would say, a management of the inverter for each car, we can maintain, I would say, the maximum current below the breakdown or the peak, and so avoid a high penalty due to that. Here I took Houdeverlee. So this is a project in Flanders. So this is a European fund. So here it's typically private houses. And what is the problem with the renewables? The voltage is not stable. So how many people who get solar panels on the roof say, oh, my solar inverter disconnects because we have maximum voltage. So, and it is true that the local distribution network have been designed with the old architecture. So that means that a transformer in the beginning of the street, and so the consumer, and the tap of the transformer was adjusted to have, I would say, upper limit at the beginning of the street and lower limit at the end. And so we have it. But now, because we inject power, so the voltage is increased, and so if you are in the beginning of the street, you reach the maximum and your inverter is disconnected. Or at the opposite, could be if you have a solar installation beginning of the street, you will increase the voltage, and at the end of the street, the inverter will be disconnected. So with a battery energy storage, we can absorb energy during big and maintain better control the voltage. So this is another application. It's not energy optimization or peak shaving. It's more voltage regulation, voltage stability. Alors, we can also, we were part also of good. I have 1 minute more, so it's nearly finished. It's nearly finished. We have also some second life battery with electrical vehicle, because when with the electrical vehicle the battery are not usable for driving because it's acceleration and brake often, but it's still totally good for peak shaving or energy solution in industry. So we participated to second life battery program. And I finish my presentation here with the diesel generator used in a railway. So I took an example with the hospital, but here it was in railway because it was control signalization for the train. So this is critical equipment which must be fed all the time. And so with the battery energy, so we could remove an existing backup generator which was working all the time, and so burning fuel all the time with the battery. So here, and we achieved this for SNCF in France. Thank you. I did already. Yeah.
Too tired to ask questions, or
no. Yeah.
What's the voltage of your battery that you always use?
Alors, that's a good question. When we provide, I would say, brand new equipment, we can select the voltage of the battery. And if we have a 400 volt network, so that means that the minimum voltage is 460 volts, but we have a range between 600 and 820, 40 volts. So we select the battery in this range. When we use a second life battery, then we cannot select the voltage of the battery. So then we may use a DC-DC converters or an AC transformer to slow down or increase the voltage to the battery. So then it is case by case to do. It is the reason why we had a R&D program with Renault, Nissan, and other manufacturing cars. It's to develop a solution which is adjusted to the battery voltage. Yeah. Question?
yeah. One question, one side.
Thank you, Mahmoud, for you saved me.
No, just to highlight, as you need, because previously in this presentation today, I saw about the MC emission. Mm-hmm. So just good to also to highlight for our product, do we meet the standards here also for the MC emission?
Alors, yeah, thank you for this good.
It's gonna link things together.
Alors, there are standards for example, the IEC 61000-3-6, which is emission in industry. So this is not a standard which was listed in the other presentation because I was looking for that. This is the maximum emission limits for industrial application, which is 8%. But this is the maximum that the utility have to guarantee. So that means that as a utility, I have to respect this, so I need to take some safety margin. So that means that I will maybe consider 7 or 7.5 or 6.5%. And after, I need to give to all my customers which are connected to my network, I need to grant you the pollution that you can emit in my network. So if I allow you 6% and that my target is 6%, that means that you have 0 because everything is taken by the first customer. So then we have what we call the planning level. And so we arrive to, I would say, you can pollute to 5% THDI or THDV, and you 4.5%, and altogether we will respect the limit. We gave some recommendation to have a THDV lower than 5%. For industrial application, it's safe. But sometimes 5% is too much. For example, in hospital, because of medical laboratories and so on, and sensitive loads, it is more than 4%. We have standards in hospital, it is 4% THGP. So then it depends of the application, and we can provide recommendation for that.
You mainly mentioned AC networks.
Yes.
What does that mean for DC sub-networks?
Alors, that's very good. So here, all the harmonics mean a multiple integer of the fundamental frequency. So that means that it is basically AC. Alors, with DC, so at present we don't have so much DC network, but we estimate that it will be very likely the future. We already have DC network, for example, in icebreaker vessel. So because the propulsion of those vessels are made in DC, and we have a DC bus, ABB, when we were, so maybe you have seen that I still have some slide with ABB.
Applications,
Yeah.
for example, we need it in hydrolyzers business, for example, but at the end we convert this to control it through our solutions.
Yeah. Today, the power is coming from AC. But in the future, I'm sure that we will have also the conducted pollution, because on the DC voltage you can have also EMC pollution. So if the where are the people from the laboratory here? I don't see. They disappeared. So we. But yeah, if we go with DC network, we will have the conduced pollution with higher frequency, and so we will have also to look at this. But here, I'm just talking about power quality with AC industry as we have today, and I guess for still a while, even we are talking more and more in buildings like here to have, I would say, DC distribution inside the building. So to still have an AC transformer or feeding line, to have a big rectifier, and to feed all the offices, because your computer, the lights, the LEDs, the beamer here are DC. We can also have DC heaters, so that's very easy.
Do I make the right assumption if I correct the power quality level of an installation by implementing an active filter, I will reduce my power consumption?
Alors, very good question. Thank you very much. I have some. We have some. I would say friends in the market say, okay, use an active filter, you will have 10% energy savings. Alléluia. Alors, this is. First, we will never at Hitachi told you such a kind of crazy things, and I will just make you a short calculation. Alors, let's imagine that you have your power transformer and you have your loads, for example, variable speed drive. You have a plant for, I don't know, bread manufacturing. This is exactly the case in Flanders, a project. And so at that time, the sales guy say, okay, dear customer, you will have 10% saving with a 10% energy savings or 8% energy savings with an active filter. Alors the customer will see dollar in the eyes. 10% energy savings. So it's a plan. Alors yeah, let's put some figures. It's a plan with, I don't know, 500, 600 people. There are 10 transformers in parallel. We are manufacturing tons of pasta. It's for bakery in the... Yeah, but it's a real case. And so here you have a feeding transformer. So losses of the transformer, big transformer, 2.5 MVA. Let's say that it is around 2.5%-ish. Okay, losses. You have a bus bar here, a very strong bus bar, but okay. You have a distribution line, switchboard, breaker here, okay. Few person losses. You mentioned that there are a lot of heat produced, but when you have a 2.5 MVA transformer, if you have 1 kilowatt of heat, it could burn your cable. With 1 kilowatt out of 2.5 megawatt, it's 0.00%. So you don't see that. And you have, I would say, a lot of motors. And let's say that the variable speed drive plus the motor efficiency, they announced in the data sheet, you can see that it is 97% efficiency. So here, losses 3%. And in the motor itself, you have also some losses. We announced, 95% of efficiency, so 5%. So that means that if you have 100 kilowatt hour of energy, kilowatt hour here, you have minus 2,5. Okay, you have 90-ish. I will take 2% just to make the... So you have an efficiency of 90%. Okay, so when you have a people who told you that you are going to have 10% energy savings, that means that you have no losses anymore. 10%, you will increase your efficiency by 10%. That means that for the same production here, you have no losses at all. So you have no losses in transformer, no losses. So that's simply not possible. That's not possible. Alors, so here the customer with the dollars in the in the eyes, okay, I need an active filter just to make a test. And so the active filter here, we were assuming a power quality filter or active harmonic filter. And we agreed with the customer to have a measurement of the efficiency. So it is the energy consumption, the total energy consumption of this line, compared to the ton of pasta produced, because from 1 month to another one, you produce 100 tons of pasta, the other one 90 tons. So we were just a ratio, tons divided by the energy, or energy divided by the ton, and so we have the energy per ton. And after 1 month, actually, we just see, I would say, 0.5% energy savings, but it was not relevant because the accuracy of the measurement was 1%-ish, so we could not say that it is an energy savings, because the active filter will also consume some energy. There are some losses inside, so the gain counterbalance the losses. And say dear customers, so that means that it was a test, and so we will disconnect the filter and bring it back. So because no, says the customer, I want to keep it, because before, when I was running my installation above 80% of the loads, all my machine was vibrating. You see the harmonic. I started to have misfiring in my PLC, and so I could never go above 80% of the load of the transformer. Otherwise, I have technical issues. Now I can work at 100%, no sound, no problem, and so on. And the fact is that instead of doing the quantity of bread in 8 hours, I just need 7 hours. But then it is a huge improvement for me because it is night worker, so that means I can reduce my team, blah, blah, blah. And so the customer installed, I would say, 10 filters, one for... But here, it's not for energy savings. Alors,
unless that you consume for 7 hours of energy instead of 8.
Indeed. So yeah, but the transformer was used at 80%, so that means that we use it at 100% or 97%. So that was okay for the network, but the production time was reduced. So the impact here was production time reduced. Alors, active filter will reduce the harmonic current. So we will reduce the current in the line because you remove the current. So there are some savings in the transformer in the line, but globally you have extra losses. So we have some cases.
You reduce the active power that you are in the grid.
Active power, normally, it's nearly the same. Yeah, reactive, yeah. So here we have some savings and we can calculate, but we cannot say that active filter we will never tell you will do some energy savings. With power factor correction, yes, and we can calculate exactly. But with harmonic,
Thank you. During a coffee and networking, you can continue. Okay?
Thank you. Thank you. Thank you.
Thank you very much.
Yeah.